All right, and the last part of our notes in section 5.4 deals with something called the remainder theorem. And the remainder theorem gives you this big, messy equation right over here, which I would imagine most of you would look at and think is total gibberish. And then we're going to try to explain it underneath, and you're probably still going to think it's gibberish, but let's run through it here, guys. P of x, which you'll notice is written in function notation, is equal to d of x. This was just how I was able to type in a multiplication sign. So it's d of x times q of x, and then plus r of x at the end of all that. Okay, what in the world is all that supposed to mean? P of x is the original polynomial function that we began with. That right there is really what's called your dividend in a polynomial division problem. That's the big messy thing that you started with. So if I go back to the very first example we did, the dividend, P of x, would be this polynomial expression right here. So P of x is all of that we started with. Okay, what's coming next? This tells us that P of x can be broken into the product of d of x multiplied by q of x. Okay, d of x, again, everybody, is the divisor. So the divisor is usually the smaller polynomial that they asked you to divide by. So this is d of x right over here. And then what happens? D of x gets multiplied by q of x. That is your quotient. Okay, so d of x multiplied by q of x should equal p of x, the original polynomial. Guys, that's exactly what I was trying to prove to you guys right over here. 7x minus 5 is the quotient, so that's like your q of x right there. We multiply that by 3x minus 4, the dividend, which was d of x, and in this case, that worked out to equal the original polynomial p of x exactly, because this problem had no remainder. But in some cases, there is this little thing that gets added at the end, so r of x is the remainder, which doesn't show up in every single problem, but certainly does show up quite a bit. And now, in the point that nobody cares that much about, here's the big takeaway of the remainder theorem. When p of x, your polynomial function, if it has a degree greater than or equal to 1, when your polynomial function is divided by x minus a, then the remainder, the thing that comes at the very end there, is p of a. Now, what does that mean? P of x is the original polynomial function, the dividend that you started with, and if you were to take out the x and replace it with a, which is the opposite of this number right here, it can give you the remainder lickety-split without having to do all that work. So let me show you guys how this works. It's kind of a cool thing, but there's also a way around it if you guys choose not to use this. So use synthetic division and the remainder theorem to find p of a. So here's the polynomial function right here. They want us to take an a value of -2 and evaluate p of -2. Okay, so what exactly is that going to look like, guys? Well, the remainder theorem says that we can simply take this remainder right here, or we can evaluate p of -2, I should say, by doing synthetic division and finding out what the remainder is. So we're going to put a number in the box. And in this case, everybody, this can be a little bit confusing. When they give you the a value right here, you don't change this number. It's exactly that number itself, including the negative sign here. So a is -2. That's what goes in the box. After that, all your coefficients. 1, and then followed by a 4, then a -8, and then a -6. No need to put any zeros right here because we didn't skip any terms. So we skip a line, we draw a line, and here we go. A little bit more practice with synthetic division. Bring the 1 straight down. And now we multiply. -2 times 1 is -2. Let's add those two together. 4 and -2 is 2. Let's keep multiplying. -2 times 2 is -4. Let's add those two together, and that gets us a -12. -2 times -12 is a positive 24. We add the -6 plus the 24, and that gets us 18. That number there is our remainder. And what we just wrote down on the last slide, guys, is the remainder is the value of p of a. So what we've just learned here, guys, is if we wanted to evaluate p, the original function, at our a value, which was -2, the answer to that is this remainder right here, which is 18. Okay, that's the answer. I'm kind of doubting you guys are like just bowled over and completely, blown away by that. First of all, we don't know that answer is right yet. I'm going to show you that right now. Second of all, I don't really know that what we just did with synthetic division is that much easier than doing this one straightforward. Let me show you what I mean. I'm going to switch to another color here. Let me go to green, I think. And let's see what happens if we had just gone straight forward here and wanted to evaluate p of -2. We would just put a -2 in everywhere there was an x in this original polynomial, and let's see what happens. -2 cubed means -2 times -2 times -2, that's a -8. Then, our next term, the -2 gets squared first. -2 times -2 is 4, times 4, that's a plus 16. Then what? -8 times -2, that's another plus 16, and then a minus 6 at the end of all that. So I don't know. Let's see here. -8 plus 16 is 8. 8 plus 16 is 24, and 24 minus 16 is 18. So it really shouldn't surprise you, I hope, that we got the exact same answer here both ways. I suppose what that does, guys, is it verifies that the remainder theorem seems to work. But the question I have for you guys is, do you think the work we initially did there in purple and in red was easier than the work that we did in green? My guess would be probably not, although there would be certain functions out there where I think what we did in green could be significantly harder, and this might be one of them right here, guys. Putting that 3 right here for a into this polynomial function could be a little bit messy. I think even I would have a hard time doing that without a calculator. Can I cheat real quick? Don't write this down here, guys, but p of 3, let's see, 3 to the 4th is 81. Everybody knows that. And 81 times 3 is 243 minus 20. Oh, boy. Okay, now this got hard. 27 times 8, 54, 108, that's a 216, gotcha. And then plus 5 times 3 is a 15 and a minus 42. So just doing this in my head, you guys, yeah, this isn't a whole lot of fun right here, let's be honest. I think we end up with a 27, plus 15 is 42, minus 42. I think I ended up with a 0, but I'm not 100% confident that I did that one right. So let's try to do it with synthetic division and the remainder theorem. This might actually be easier. So I draw myself a box, and remember, guys, when we're doing the remainder theorem and they tell you what a is, you don't change a sign right there. 3 is what goes there. Now, all your coefficients. We have a 3x to the 4th, then a minus 8x cubed. There's no x squared term, so there's going to be a 0 that goes there. Then a 5x, and then a minus 42 at the end for the constant. Skip a line, draw a line, and here we go. We bring the 3 straight down, and we start multiplying now. 3 times 3 is 9. We add these two terms together and get 1. Okay, 3 times 1 is 3. Adding 0 plus 3 gives us a 3. 3 times 3 is 9, and the 5 plus the 9 is 14. 3 times 14 is positive 42. We'll add those together. And sure enough, we ended up with 0. That's your remainder, and the remainder gives you the value of p of a. So our answer here, guys, p of 3 is equal to whatever this number is right here, which in this case is 0. So now I'm going to ask yourself again, guys, realistically, what would be easier for you? The way I did this problem first right here, which involved a lot of math that I had to do in my head, or doing it this way right here with synthetic division? I think if you're being honest with yourself, that second way is probably the way you guys are going to be more likely to get the correct answer. It doesn't look like the first way was very hard, but that involved a lot of mental math that I wasn't even 100% sure on. I think you guys would struggle with that. The second way took a little bit more writing and maybe a little bit more time, but nothing that we did right there was all that difficult in terms of mental math. So with a big messy polynomial like this, I think this second method of using synthetic division and the remainder theorem worked better than just the straight evaluation of the function that I did there in green. Okay, guys, that's how the remainder theorem works. That's all I got for you for 5-4, so let's dive into that homework, and good luck, everybody.